Hello student, in this lecture we will discuss about the binomial heaps. Binomial heap is a collection of binomial trees, and a binomial tree which is denoted as BK is an ordered tree that is defined recursively. Recursively means a, a tree BK is defined in terms of tree BK minus 1, and BK minus 1 is further defined in terms of BK minus 2 up to B naught. Okay, where K denotes the degree of the root node. A binomial tree B naught consists of a single node, as you can see in this figure. This is B naught, and B naught contains only single node, while B1 is a combination of two B naught, one B naught, and this is another B naught, and these are combined together. That means one B naught becomes the child of another B naught. Similarly, B2 is the combination of two B1, and one B1 tree becomes the leftmost child of another B1. That means B2 can be defined in terms of B1, and B1 in further can be defined in terms of B0, and the smallest one binomial tree is B0, which consists a single node. Okay. Now the root of one is the leftmost child of the root of the other. That means as we have already discussed, BK is the combination of two BK minus 1, and one BK minus 1 tree becomes the leftmost child of another BK minus 1. As you can see here in this B2, okay, B2 is a combination of 2B1, and this is 1B1, or this is 1B1, and the leftmost child of this B1 is this B1. Okay, so as per the definition, one BK minus 1 becomes the leftmost child of another BK minus 1 in order to become the binomial tree BK. And these are the several examples of different binomial tree of different size, such as B1, B0, B1, B2, B3, B4. Okay, now if you look at the B4, it contains 16 nodes, that means 2 to the power 4 nodes, 16 nodes, and these are the depth of different nodes. This is depth 0, depth 1, depth 2, depth 3, depth 4, and mind that 4 is the maximum depth and 4 is the degree of it. That means the depth of the binomial tree as well as the degree of the root. This is the degree. Degree denotes the number of children of any node. So root node has 4 children: first, second, third, and fourth. Okay, so degree of this root node is 4. That means K denotes the degree as well as the depth of the tree. Okay, so move further. Let's discuss some properties of binomial tree. These are very important and generally asked in the exam. Write down the properties of binomial tree, and we have only 4 properties. First property, as per the first property, there are 2 to the power k in a node, or there are 2 to the power k node in a binomial tree BK, where k denotes the degree. Now for B0, value of the k is 0, and in that case number of node would be 2 to the power 0, which is 1. So in B node we have a single node. If the value of k is 2, that means B2 will contain 2 to the power 2 nodes, that means 4 nodes. This is again 2 to the power 4 nodes. Okay, the height of the tree is k. Height of the tree is k. As you already know, the height of a root node is the number of edges, number of the maximum edges which are required to traverse to reach the leaf. In case of this B3, look at this B3. This is the for this root node, this is the first edge, this second edge, this is the third edge, and this is the farthest leaf node for this root node. That means the maximum length is 3. That's why the height of this tree is 3. And as per the third property, there are exactly KCI. This is written like this: KCI. Okay, KCI. There are exactly KCI nodes at depth I for I is equal to 0, 1 to K. Okay, now let's verify this. For depth 1, let's find for this particular tree B4, if we want to calculate number of nodes at level at depth 1. Okay, as you can see in this figure, these number of nodes are 4. By using this formula, if we want to calculate, it would be 4c1, and the value of this 4c1 is factorial 4 upon factorial 1 and factorial 3, and it would be 4. So 4 denotes the number of nodes at depth 1. Similarly, if you want to calculate the number of nodes at depth 2, it would be 6. Okay, so value of 4c2 would be factorial 4 upon factorial 2 into factorial 2. Okay, now it would be 6. Okay, so number of nodes at depth 2 is 6. Now come to the fourth property. The root has degree k. As I already told you, the degree denotes the maximum number of children a node can contain. So in this example B4, in this tree B4, root has 4 children, 1, 2, 3 and 4. That means degree of this node is 4. So root has degree k, which is greater than any other node. So look at any other node. This node has the degree 3 because it has 3 children. This node has degree 2 because it had 2 children. This node has degree 1 because it has 1 child, and this node has degrees because it doesn't contain any child. Okay, more if the children of the root are numbered from left to right, k minus 1, k minus 2 up to 0. So for this root node, leftmost child is this. Okay, and this contains 3 nodes, 1, 2, 3. That's means degree of is 3. And for this node it is 2, and for this node it is 1. So degree goes from k minus 1 to 0. Okay, so let's read it again. The root has degree k, which is greater than of any other node, more if the children of the root are numbered from left to right by k minus 1, k minus 2 to 0. Child I is the root of the subtree bi. Okay, the maximum, the important thing, the maximum degree of any node in n node binomial tree is log n. This is very important, log n. As you can see in all these trees b0, b1, b2, b3, b4, okay, the number of nodes are 2's power k. Okay, and root has the maximum degree. In b2 this is the root and it has degree 2 and value of k is 2, that means degree is 2. And for b3 root has the degree 3 because these are the 3 childs, and for b4 root has the 4 children. Okay, so degree is equal to k and number of nodes are 2's power k. 2's power k is the number of nodes, and this is the number of nodes. Okay, let's say nodes are n. So k denotes also degree. So let's take on log both side, and if we take log both side, the value of k would be log n at base 2. So k is the degree of binomial tree bk, and value k is log n, where n denotes the number of nodes in that binomial tree. As per the first definition, number of nodes in the binomial tree bk are 2's power k. That's why I have written 2's power k is the number of nodes which are n. or after taking log on both sides, k becomes the log n. So maximum degree of any node in binomial tree is log n, and the maximum degree is always of root node. Okay, now come to the binomial heap. A binomial heap is a set of binomial trees that satisfy the following two heap property. Now first, as per the first property, each binomial tree in H obeys the min heap property. As per the min heap property, the key of a node is always greater than or equal to the key of its parent. Now we can say that a such tree is a min heap order tree. That means that order is maintained by the, as we have did in the min heap. Okay, so value of the parent is always less than equal to its children. Okay, for any non-negative integer k, there are at most one binomial heap in H whose root has degree k. This is very important. It says, as per this definition, binomial heap is a collection of binomial trees. Okay, now these binomial trees are min heap orders. That means in each and every binomial tree there is some order, and order is that value of each node is always less than equal to value of its any child. Okay, now as per the second property, if binomial heap is a collection of several binomial trees and each binomial tree has some degree, and that degrees should be unique in that particular binomial heap. Okay, now look at this example of binomial heap. This is simple binomial heap. In this binomial heap we have three binomial trees. First is b0, this is b2, this is b3. Okay, this is b0, this is b2, and this is b3. So this binomial heap contains three binomial trees, b0, b2 and b3, and in b2 root node has value 1 and its both children had 12 and 25, and this 12 has one child which has value 18. That means this binomial tree follows the min heap property. Again look at this binomial tree b3. Okay, now b3 has value 6, okay, as a root node, and it has three children which has value 8, 14, 29. That means values of all children are greater than 6, and 8 again has two children 11 and 17, both are greater value, and 14 has one child which has value 38, and 11 also has one child which has 27. That means all nodes follow the min heap property. Okay, now there is a special pointer that is called head H, which points to the first node in the root list of this binomial heap. This as per the definition, binomial heap is a connection of binomial trees, and this binomial tree is connected with the linked list which connects the root of each binomial tree. That means some people says that it's a root list. The first root of b0 is 10, root node of b2 is 1, and root node of b3 is 6. That means these are connected with the help of a linked list, and there is a special pointer called head H which points to the first node in this binomial heap. Now as per the implementation purpose, now each node in this binomial heap contains these structures. That means following fields are available each and every node of a binomial heap. First one is the parent. This value points to the parent of that particular node. If it is not available in case of root, that means it is null. Key denotes the value which is stored in that particular node. Degree denotes the number of children available to that particular node. Child is a special pointer that points to the leftmost child of that particular node. Sibling denotes the right node at the same level of another binomial tree. Okay, so these 5 fields are used in each and every binomial heap node. Okay, now again, now let's take a small analogy now which would be beneficial in further discussion. Now look at this binomial heap. This heap contains 408 plus 412 13, that means 13 nodes. Okay, if I denote the 13s as a binary number, okay, if I denote not 13 as a binary number, it would be 1101, and this is B0, this is B1, this is B2, this is B3. Okay, now this binomial heap contains 13 nodes, and if I represent these 13 number in a binary equivalent, it would be 1101. Now if I want to find out that in 13 node size binomial heap which binomial trees would be available, then I find out with the help of this analogy. Okay, now you have to check out, you have to start from the right hand side. This is B0, this is B1, this is B2, and this is B3, and so on. Okay, number of digits would depend on the size of the binomial heap. So in our case it is 13, so that means 4 digits are required to represent 13 number. These are the sequence of the digits. Now in order to find out which tree is available and which would be not available in this binomial heap, you have to look at this. If it is 1, that corresponding digit tree would be available in the binomial heap, and if it is 0, that particular size tree will not be available in that binomial heap. So look at this. This is B0 1, so B0 is available. B1, for B1 it is 0, that means B1 would not be available. For B2 it is 1. Now, so this is our B2, and for B3 it is 1, so this is our B3. So this small analogy would be beneficial when we do our further analysis. Okay, now this is the graphical representation of binomial heap. This is the same binomial heap which we have discussed previously. Now look at this binomial heap. This is B0, this is B2, this is B3. Now this is for parent. For this root there is no parent, that's why it is null. This is the key value 10. This is the degree. Degree denotes the number of children because it has its size is B0. It has single node, no child, so that means it is 0, and there is no left child available, so null. And this is for the sibling. This is the root list. Root is another node. Now look at this B2. For this particular node B2, for this particular node of binomial tree B2, parent is not available, it is nil. Value of this is 1, value of the node is 1, and the second is 2 is denotes the degree of this particular node. Degree, that means two child nodes are connected to this, and there is a special pointer left which points to the leftmost child of this root list. So this is the leftmost child of the root list, so it points to this. And sibling, for the sibling it points to the next node in the root list. Now come to this node. For this particular node, okay, the parent is this, 12 is the key value, 1 is denotes the degree because it contains one child, and there is one child point to this, okay, and the sibling denotes to this. That means sibling, for the sibling is a special field which point to the next node at the same level, okay, similar B3. So this is a graphical representation of binomial heap. Hello student, in this lecture we will discuss about some operations on binomial heap. Okay, now as we have already discussed in last lecture, a binomial heap is a collection of binomial trees, and there are 4 properties of binomial tree, and that particular binomial tree is defined recursively. Okay, after that we took the analogy of a binomial heap. If a binomial heap contains n number of nodes, we can easily find out the in that particular binomial heap which particular binomial tree would be available or not, and we already done this exercise in last lecture. In this lecture we do 2 operations on binomial heap. First one is the finding the minimum key in the binomial heap, and second operation is the union of 2 binomial heaps. So let's discuss finding the first operation, finding of the minimum key. Okay, now the procedure binomial heap minimum returns a pointer to a node with the minimum key in a n node binomial heap H. This implementation assumes that there is no key with value infinity. What does it mean? It means that all the values available in the binomial heap are lies in a particular domain. There is minimum value and maximum value, and all values lies between these 2 values. Okay, and if we talk about the infinity, we can consider that infinity is a very large number. Okay, now as we already know or discuss, in binomial heap all heap follows the min heap property. That means each and every node in a binomial heap follow the property that the value of that particular node is always less than equal to its children. Okay, now as we already know, binomial heap is a collection of binomial trees. Okay, now binomial tree, in each binomial tree the minimum value node would be at the root. Okay, and we already know that in binomial heap root of all trees which are available in the binomial heap are connected with the root list. That means for each and every tree the minimum value of that particular corresponding tree would be available in the root list. Okay, now if we are interested in finding out the minimum value node in the whole binomial heap, that would certainly will be available on the root list. That means we have to search that particular root list in order to find out the value of the minimum key node. Okay, now let's calculate the length of that particular root list. As we have already took the analogy of binomial number, okay, of number n. Let's say in a binomial heap there are total number of nodes n. If we convert that particular number into binary number, that would represent the total number of trees available in that particular binomial heap. We already done that exercise. Okay, now the number of bits required to represent a decimal number into a binary numbers are log n. That means if we know the number of n, then we can find out the number of digits. That simple formula is log n. So the length of the root list is log n. Now if we find out minimum value In a root list we have to, but the simple exercise, we take the first node as a, we consider the first root node as a minimum value and compare it with the next one. Okay, then if the next value is smaller than the current mean, then we change the minimum value mean, otherwise we keep consider the first value is a minimum and do it again with the next node and so on. So total number of comparison would be log n, because length number of items in the root list are log n. So it is very clear that complexity of this particular exercise would be log n. Now look at this simple algorithm which is given in your book, which can find out the minimum value in your binomial heap. So first of all, binomial heap mean h, that means you have to pass your binomial heap in this particular procedure, and where h denotes the head of that particular binomial heap. Okay, now let's consider a variable y which initially points to a nil, and there is a one more variable x which initially points to the head h. That means head h is used to point the first node in the binomial heap in the root list. So x also points to that node. Now take a variable min, initially it is initialized to infinity, and now there is one loop from line number 4 to line number 8, and in this while loop we do some comparison, and this while loop executes until x doesn't becomes nil. So initially let's consider the binomial heap is not empty, so x is not empty, and now key of x, please note that x denotes the initial node, root node, and key is value available in that. So if that value is less than the current mean, initially current mean is infinity, okay, other then we change the minimum value, okay, otherwise we do nothing, and find out the sibling of x. Sibling of x denotes the next node in that particular level, that means next root node. Okay, now it become x again while x is not nil, and a key of x is less than the current mean, then change the min with the new value of x, and that x will become the y, and again find out the sibling of x. This loop goes until unless x becomes nil. So you can see that this loop is accessing the each and every node which are available on the root list of the binomial heap, and in the end it will return y, which denotes the minimum value. And as we have already discussed that complexity of this exercise is log n.